I'd like to talk about the general steps to finding the zeros of a polynomial and graphing the function, just so you kind of see where our goal is headed here. We're going to be doing a little bit of rational zero theorems to try to find some possible zeros, and it's kind of a good idea to know what the big picture is so that you can see the end in sight. If I am given f of x equals a sub n x to the n polynomial with lots of terms here, I know that looks a little bit scary for a lot of students, but all you really need to know is x to the n means an nth degree polynomial. It could be the fourth degree, it could be a fifth degree, or so on and so forth. What I want to do is take that large polynomial and I want to be able to factor it. So that's the first step here. Factor the polynomial to get the product of linear factors. Once I get the product of n linear factors, then that will tell me the roots and the zeros. That's step 3. Once I have the zeros or roots, I can then graph using end behavior. To the right we have an example. So first I start off with some large polynomial that I may or may not know how to factor at this point. Then I'm going to factor it into n, or 3, because the degree is 3. I have 3 linear terms. Once I've factored that, I can find the zeros or the roots. Then I can place the roots or zeros using end behavior, and I can sketch the graph. So that's kind of my goal here. This is basically the same steps that we talked about in the higher order polynomial functions and how to graph them. The only difference is when we're asked to factor from this first line to the second line, it was always easy. It was really easy to factor those because we could just use the factoring methods that we had learned in previous classes. In this section, we're going to be using much higher order polynomials with harder factoring problems, and this is now going to be the hard step. If you can't factor, so if you can't factor easy, this is now the hard step, okay? Being able to factor into polynomials is going to be the hard step, which is why we talked about on last lesson synthetic division. We will be using synthetic division to take this large polynomial and to divide it out so we have a product of linear factors. The only problem is where do we start with synthetic division? Okay, and that's the real question. What factors do we try to divide? Remember, in synthetic division, in the problems that we worked there, you were already given, hey, given that this is a 0, factor the rest of them and find the 0. Given that this is a factor, you try the rest. So the hard part of this section is, I'm not going to tell you what the first 0 is. I'm not going to tell you what the first factor is. You're going to have to figure that out on your own. That is the very difficult part of this section. The rest of it is kind of like a review, putting together pieces of the last few sections, putting it together in order to factor and graph very hard polynomials with high order. So that's the question we want to answer first. What factors do we start to try to divide in order to find a 0 remainder so that I can truly factor this? So that's the next thing that we're going to talk about. Before we actually get to this, we're going to stop and look at rational zero theorem. To find zeros, when you are not given a first factor or the first 0, we're going to need to use the rational zero theorem, which says if we have a polynomial of nth degree, and this is just the math way of writing an nth degree polynomial in which we don't really know what it is, then all of the possible rational zeros of f of x are equal to the factors of a sub 0, or a naught, divided by all of the factors of a sub n. Another way of writing that would be the factors of the constant term divided by the factors of the leading coefficient. And what this is going to get you is the possible rational zeros. possible rational zeros. Now I underlined that because it's so important that you understand what does possible rational zero mean. So we're going to go even one step further and just discuss what does it mean possible. It means that this function may have one or more rational zeros from this list, although a function may not have any rational zeros. That's what possible means. If it is rational, then it is in this list. But I can't guarantee that there are any rational. I can't guarantee there's one or two or three or any, really. It just means it's the list of possible. The second thing I want you to understand, what does rational mean? A rational number is any number that can be expressed as a fraction, which then must be real. I know that seems a little bit silly. All rational numbers are real, and I know we've talked about that in previous classes, but I want you to make sure that you understand that this list only lists the rational numbers, which are real, which means it leaves out all the complex and all the irrational. So we may have more zeros that aren't in this list that are irrational or complex. But what this rational zero theorem does is something pretty darn amazing. Remember when we set up here at the top, I said, how do you factor? Well, I don't know. We'll just start picking random numbers to divide, synthetically divide? Well, that's not really time efficient, just to start picking 1, 2, 3, is 1 a 0? I don't know. Let's try it. Synthetically divide. Is 2 a 0? I mean, that's going to take you a really long time to be able to figure out what the first zero is. What we are doing is we're taking an infinite amount of possibilities. If we don't even know what the zeros of some random polynomial function are, well, then I can at least tell you what the possible rationals are, and then we'll just start picking from that list. And even though that seems like a daunting process, we took an infinite amount of possibilities, and we're taking them down to a very small group of numbers. Even though it may seem a little bit large to you if you have to try 2 or 4 or 6, possibly 8 different synthetic division processes to get the factor, at least you don't have an infinite. And this is quite amazing to me. This rational zero theorem takes an infinite process down to a finite process, which is very, very, very helpful, which we'll see in a little bit. The next example I want to show you is I want you to use the rational zeros theorem to list all the possible rational zeros. Again, we're not guaranteeing that the possible rational zeros list will have a zero in it. It's just all the possible rational ones that we could have. So in this first polynomial, f of x equals negative x to the fourth plus 3x squared plus 4, my constant term is 4, and my leading coefficient here is 1. So the possible rational zeros are the factors of 4 divided by the factors of negative 1. The factors of 4 are going to be 1 times 4, so we'll say 1 and 4, or 2 times 2, but I don't really need to write 2 twice. Can you think of any other factors? And we didn't say they had to be positive, so we can actually include negative factors. We could have a negative 1 times a negative 4. And we also have a negative 2 times a negative 2. So not only do we need to include the positive numbers, but we also need to include the negative numbers. Now what are the factors of negative 1? Well, the factors of negative 1 are 1 times negative 1 or negative 1 times 1, which includes, again, positive or negative 0. And some students usually ask me at this point, does that mean that every factor in the numerator and denominator are going to have a plus or minus? Yes, it does. Everyone will have a plus or minus because the factors could be positive or negative. So what we're going to do now is we're going to take each of the terms in the numerator and divide it by each of the terms in the denominator. Fortunately, this time we only have one term in the denominator, so 1 divided by 1 is going to be plus or minus 1. 4 divided by 1 is plus or minus 4. And then 2 divided by 1 is plus or minus 2. And this is the list of possible rational zeros. So what that means is if f of x has a rational zero, then it will be in this list of 6 numbers. What we just did is we took an infinite amount of possibilities for 0 and broke it down to a possible 6 for at least the rational zeros. That right there is pretty amazing. Let's do it one more time for the next problem. F of x is equal to 15x cubed plus 14x squared minus 3x minus 2. And I'm looking for the possible rational zeros. I know that I'll have 3 zeros, but all I'm looking for is just a list of the possible rational ones, which means I'm going to take the factors of negative 2 and divide them by all the factors of the leading coefficient 15. It's always the factors of the constant term divided by the factors of the leading coefficient. The factors of negative 2 are 1 and 2, plus or minus 1 and plus or minus 2. The factors of 15 are plus or minus 1, 1 times 15, 3 and times 5, so plus or minus 3 and plus or minus 5. And that looks like it's it. Although, when you're looking for the list of possible rational zeros, you have to take each of the factors of the numerator and divide it by each of the factors in the denominator. I don't really care what the order you do this in, I just try to make sure that it's a little bit organized so you don't miss one. How I'm going to do this, I'm going to take negative 1 and I'm going to divide it by each of the denominators. Then I'll come back and do 2 and divide it by each of the denominators. So for now, 1 divided by 1 is plus or minus 1. 1 divided by 15 is plus or minus 1/15. 1 divided by 3 is 1/3, and 1 divided by 5 is 1/5. Next, I'm going to come back and take the plus or minus 2 and divide it by each of the denominators. 2 divided by 1 is 2. 2 divided by 15 is 2/15. 2 divided by 3 is 2/3. And 2 divided by 5 is 2/5. And that is my list of possible rational zeros. We have 1, 2, 3, 4, 5, 6, 7, 8. That means we have 16 total possible rational zeros. If I was to try to factor this, I would just start picking from this list and synthetically dividing by the zeros to see if I have a factor, and then I can factor it down. So that is an example of using the rational zeros theorem to list all the possible rational zeros for any polynomial function.